Alright, let's talk about complex numbers. So up to this point, we've said that the square root of a negative number is undefined because there's no value that can be multiplied by itself to get a negative value as an answer. However, we're now going to extend our concept of numbers to include a new value, which we label with an I, and is defined as the square root of negative 1. The complex numbers are a new system of numbers which are going to encompass all real numbers and imaginary numbers as well. So everything we know up to this point still applies. We're just extending ourselves. So a complex number is generally written in this form, where we have A as the real part of the complex number and B as the imaginary part. And when we say imaginary, don't think too much into that. It's not that we're making stuff up. There actually is very good real-life applications of these. Basically, we're just separating the two different types of numbers. We have the real number and what we call the imaginary number, together making up the complex values. So to show you how this is going to help us with solving things, so for instance, in the past, if we had the square root of negative 4, we would have said that that's undefined. However, now we can say that this is equal to 2 times I. So what's happening is we're basically splitting this up into negative 1 times 4, and then the square root of negative 1 is the value I, the square root of 4 is 2, and instead of writing I times 2, we express it as 2I. So effectively, anytime you have a negative underneath the square root, you just pull out I from underneath the square root. All right? Let's say we have the square root of negative 3. Well, 3 is not a perfect square. That's fine. We just reduce the square root as best we can, and then pull the I out, or the negative out as an I. And in this case, we do put the I in front of the square root, because if we put it behind there, depending on how you write your square root, might actually look like it's under there, or it might not. So we just put the I in front just to make it a little bit more readable. Okay. When solving quadratics, you can end up with parts that look something like this. And in those situations, to simplify, you just simplify the radical. In this case, 11 is a prime number. Can't do anything else with it, but we can pull that negative out as an I. And that would be the simplest form of that particular answer. Or let's say we're solving this equation. Now, up to this point, we've said that, we have the difference of squares, which might look like x squared minus 9, which we could factor into x plus 3 times x minus 3. And we said that the sum of squares is not factorable. We basically called that a prime polynomial. However, it actually is factorable. It just happens to be factorable into the complex numbers. So this is actually x plus 3i, x minus 3i. So what happens here when solving this, if you subtract 9 from both sides, that cancels the 9 out. You now have x squared equals negative 9. If you take the square root of both sides, the plus or minus square root of negative 9, which is plus or minus 3i. All right, let's take a look at some operations on complex numbers. Now, addition and subtraction are pretty straightforward because you just do the individual real part and imaginary parts separately. So let's say we have this as a problem to solve. So 2 minus 4i plus 7 minus 10i. All you're going to do is just basically combine your real parts and then combine your imaginary parts. And leave them separate in the end. So this would be 9 plus, this becomes negative 14i. So we have 9 minus 14i. Okay, one more example of that. Let's say we have negative 1 minus I minus 15 plus 2i. So we will combine our real parts and imaginary parts. So just separate them for the time being. And I'll do plus negative I minus 2i. Now notice I have minus 2i because this negative distributes to both pieces inside that parentheses. So this becomes negative 16 minus 3i. All right, now for multiplication, what we do is use the process of FOIL. So multiplication gets to be a little bit difficult when it comes to complex numbers, but I'll show you the process here. In the end, we generally don't need to do multiplication a whole lot on complex numbers, so you don't need to worry about doing too much of this, but you do need to know the process just in case. If we FOIL these out, I could start by doing 2 times 3, which would be 6. Then 2 times I, which would be plus 2i. Negative 2i times 3, so minus 6i. Then negative 2i times I. This is going to be negative 2i squared. Now, I squared, let's look at that. If I is equal to the square root of negative 1, well, let's say I square both sides of that equation. So this would be I squared, and if I square a square root, the root disappears, and so I squared is actually equal to negative 1. So this is going to be 6. I'm going to go ahead and combine 2i and 6i, so minus 4i minus 2 times negative 1. So 6 minus 4i plus 2 gives me my final answer of 8 minus 4i.
When it comes to the division of complex numbers, I don't know of any long division or process such as that really works, although there's probably something out there. What we'll do instead is a process similar to multiplying by the inverse. It's not exactly that. What we're going to do is take advantage of what are called conjugate pairs. Conjugate pairs are binomials where you switch the sign of the terms in between. So for instance, 1 plus I is a binomial in the denominator. Its conjugate pair is 1 minus I. Same terms, I just change the sign in between them. And what's important about that is when I multiply, I'm going to use the process of FOIL, and it will eliminate the complex value for me. You'll see as we go through the example. Now, I can't just divide by 1 minus I without doing the same in the numerator. So to balance things out, I'm going to multiply the numerator by 1 minus I as well. Okay, so let's start with the denominator so you can see how the complex value cancels out. Using FOIL, I'll take 1 times 1, which is 1, and then 1 times negative I, which is negative I. Then I times 1, which is positive I, and I times negative I, which is negative I squared. And if you'll notice, I have a positive I and a negative I. Those are going to cancel each other out. That's what was important in the setting up this difference of squares. The I squared is going to disappear as well because we know that I is equal to the square root of negative 1. If you square both sides of this equation, you get I equals negative 1. Sorry, I squared equals negative 1, which means we're going to be able to replace that with a real value as well. So the entire denominator will be real numbers. In the numerator, we also need to use FOIL. 2 times 1 is 2. 2 times negative I is negative 2I. Negative I times 1 is negative I. Negative I times negative I is positive I squared. Okay, simplifying here. In the numerator, I have negative 2I minus I. Since they're both imaginary values, I can combine them into negative 3I. I squared, as I just showed, can be replaced with negative 1. So for right now, I'm going to express that as plus negative 1 for emphasis, but that's not something that you necessarily have to do. Then in the denominator, 1 minus, those i's canceled in between, but I have still negative I squared, so it's going to be minus negative 1. Now, 2 minus 1 is 1, and negative 3I still exists there. And 1 minus negative 1 is the same thing as 1 plus 1, which is 2. And your final answers, generally you want those expressed in terms of a complex number that looks like z equals a plus bi, where a is your real part, b is your imaginary part. So we want to separate this through division. So it's going to be 1/2 minus 3/2 I. And that's our final answer. That's the two values divided.
So we already know a couple of these. So I to the first power is just I. That's kind of given to us from the beginning. And we looked at I squared and discovered that that was negative 1. We can go on with this. Let's say we want to figure out I to the third power. Well, I to the third power would be I times I squared. So I times negative 1, which is negative I. I to the fourth power is the same thing as I squared times I squared, or negative 1 times negative 1, which is actually positive 1. So if you continue with these, like I to the fifth power, this basically then is I to the fourth times I, which is just I to the sixth would be I to the fourth times I squared, which would be negative 1. This actually repeats in a cycle. So once you get to the fourth power, this is kind of all the different values you see for powers of I. But in case, generally you only run into I to the first power and I squared, but just in case, this is how you would come up with the rest of them. Now, I'm going to show you how you can use your calculator, because in this class, you're not really required to do a lot of complex values just on your own. So I'll bring up the calculator and show you how to do this, but the things you want to kind of know from the beginning is you need to set your calculator mode to complex. so that it outputs values of a plus bi. And always use parentheses when you're doing a multiplication and division, otherwise you'll get incorrect results. So let me pull up the calculator and show you how this is done. Okay, so I'm assuming that you're using either the TI-83 or TI-84 calculators. That's the recommended calculator for the class. Most other scientific graphing calculators have the same basic functionality, but you're kind of on your own to figure out how they work. So I would really recommend using this because I can just bring it up on screen and show you exactly how to use it. So after you turn it on, you need to change your mode setting to where you have complex numbers available to you. You kind of scroll down just a little bit, you see where it's real that's flashing. So I'm in real numbers. And in that situation, if I do the square root of -1, it tells me the answer is non-real. So I get an error message. But let me change my mode to complex, so the a plus bi. This is also a form of complex numbers, but you won't see those until trigonometry really. So this is what you want right here. So just hit, once you have that selected, second and quit. Now come over and try the square root of -1, and you end up with I. So now it's working with complex values. So if you want to say add, so 2 minus 3, if you do second and your decimal place, you can bring up the unit I. And then say I want to add that to, let's do -1 minus 6i. And one thing I will say here, notice the difference between the negative symbol and the minus. This calculator differentiates between the two, so if you put a minus where you mean to put a negative, you'll get an error message. Eventually you get used to it, but it takes a little bit of time. So it just takes the real parts and imaginary parts and combines them as it should. Now the big advantage here is, let's say you want to multiply. If you do 3 minus I times -1 plus I, and I put parentheses around my numbers. I went ahead and did it when I was adding as well, just to emphasize what was my first number and my second number. It's not really necessary when adding, but it's definitely necessary when multiplying, because if you don't, then it won't FOIL the numbers. So it goes through, does the operation of FOIL, simplifies, gives you the answer, no problem. And even if you're doing division, it does that pretty seamlessly as well. Just make sure, again, you're using parentheses around your complex numbers, and then it'll give you your answer in the end. Now, if it gives it as a decimal, I know this works in real numbers. I assume this works in complex numbers as well. If you hit the math button and the first option here is an arrow with frac, it means to convert the answers to fractions, and that can be a helpful piece at different points. Now, most of my videos I'm only going to show you how this works with the TI-83. There is some small differences in the TI-84. I'm going to pull it up and show you right now what that is. But from here forward, I'm just going to be using the TI-83 because everybody has that compatibility. So let me bring up the 84. Okay, and here's the 84. If you go into the mode settings, it's basically the same. There's just more of them, but you have the real and complex modes, so that works the same. But you have another page of them as well. And the only thing that's really different is this option called Math Print versus Classic, and then this is for fractions. If you want your calculator to look exactly like what I'm seeing, if you've got the TI-84, set your mode here to classic, and then I guess just leave this as is. And so, you know, now let's say I do like 3 minus 4i. All right, and then I want to multiply that by 2 minus I. So all the functionality is the same there. Fractions. Okay, yeah, it's doing the fractions the way it should be. The difference is if you have that math print like this. Oh, it's not doing it. Never mind. Anyway, there's a way that you can get it to make it look like a fraction, but it just sometimes becomes more confusing with teaching students the different calculators. I think it's best just to set your calculator back to the default to operate just like the TI-83. So, and then there's some of you with the color calculator. It works basically the same. It just looks a little different as well. So if I pull that up, get the mode, you just have more options. But here's the real. Switch it over to the complex, and then you can go from there. All right.